Well, this video is going to be Chapter 5 for the Netacad CCNA Course 1. It is going to be a one-part video. So Chapter 5 is just going to be one video. It may be a little bit longer than a normal video for on here, but I believe I can get everything in one video and not having to break it into two smaller ones. So this one's going to cover Chapter 5. It is the version 5.1 of the Netacad course material, and if you want the 5.0 videos, there is a link down in the description on those. My name is Jason Johnson. Thank you for watching. If you find any information in these videos helpful and you want updates on future videos, just click the subscribe button below. And if you have a question, you can just leave a comment below. Those are always welcome, and feedback is welcome as well. So let's start with Chapter 5, and we're going to talk about Ethernet in Chapter 5. And we're going to do this all in one shot. So we're going to talk about Ethernet protocol, LAN switches, ARP, or Address Resolution Protocol, and then we'll have a summary. So when we're talking about the Ethernet protocol, what is the Ethernet protocol? And we're going to talk about Ethernet sublayers and the Ethernet MAC address. So the Ethernet frame, when we look at a frame, an Ethernet encapsulation or an Ethernet frame, it's defined by the data link layer and the physical layer protocols. So the physical layer protocols and the data link layer, the MAC address is this section here, or the Ethernet is these two sections here. And then when we're looking at the OSI layer here, 1, 2, 3, 4, 5, 6, 7, on up. I'm not going to put labels all the way up, but when we're looking at the layers, you should, for this course and for learning networking, you should just in your mind, you should just immediately know when you're talking about a certain layer what number that is, because you're gonna hear in the industry, and you're going to hear terms. You're going to say, well, that's a layer 3 device. Well, you just need to know that that device is working at the layer 3, that it has some type of routing device, or it's a layer 2 device, and that's some kind of switch. So as you learn this material, you're going to learn that you just need to know what layers each one belongs to and what they are on these. So let's talk about it from a just the text point here. It's the most widely used LAN technology, Ethernet is. It operates in the data link layer and the physical layer. There's a family of networking topologies, and they're defined by the IEEE. Remember, we talked about organizations in earlier videos, and the IEEE governs the 802, 802.2, 802.3 standards, and you can go look those up on the internet. The 802 standards or the IEEE standards, and read more about those. But they support data widths from 10 all the way up to 100,000 megabytes or 100 gig. The Ethernet standards, again, define the layer 2 protocols and layer 1 technologies, such as your copper wiring and your twisted pair, unshielded twisted pair, which we looked at in the Chapter 4 videos. There's two separate sublayers of the layer 2. You have the logical link control, or the LLC, and the MAC sublayers. From a graphic standpoint, if we're going to look at it from a graphic here, you have the network, layer 3, your layer 2, and your layer 1. And so your physical layer, you have your Ethernet, your IEEE governs those, your standards in there. And you have your LLC sublayer and your MAC sublayer. So if you're just doing a layer 2 and it's just staying in a layer 2, you would just use your MAC addressing and your MAC sublayer on there. And if we're looking at it, the primary responsibilities for the MAC sublayer is broken down in here. You don't need to really memorize all of this information here for the Netacad course, but you need to be familiar with it. You may see a question on it. You may see a question on the actual number, the 802.3, and which layer is that? And that's at a layered. The media access control is at the layer 2, but you don't really need to memorize all of the whether it's a DB9 or an RJ45 or a fiber optic SC connection, and you don't need to memorize all of those, but you do need to be familiar that that's what layer they operate. They are in this layer or they are in this area. So when we're looking at a frame for the Ethernet, we are looking at our bytes of information here, and remember 8 bits is a byte, so then 8 bytes. You can calculate that on it. So we have 8 bytes of information. That's our preamble, and that's just telling the node, or that's telling the network, hey, I've got a frame that's coming your way, and this is the first 8 bits of data, 8 bytes of data, excuse me, your first 8 bytes of data, and then you have the following 6 bytes are your destination address, the next 6 bytes are your source address, 2 bytes of your type of the frame, and then you can have anywhere from 46 to 1500 bytes of data, depending upon how big that is. And the max size would be 1500, and then anything larger than that would be broken up into multiple frames. So if you're sending a gig worth of data, that's going to be broken up into many different frames. But that data resides right here, and then you're going to have your frame check sequence, and that's 4 bytes of data. 4 bytes of data. I can't pronounce that properly. 4 bytes of data, and that's the frame check, just to say, hey, did you get all the information? My preamble said I should have had X amount of bytes in here, including the data, and so I should have had X amount of bytes coming your way. Did all of those go through? That's the frame check sequence, and it's going to check and say, did all those get through? And it's going to frame check, and then it's going to resend if it didn't get the right amount, or if it did get the right amount, it'll accept and then keep moving on. So the minimum Ethernet frame size is 64 bytes. That's a collision frame, or what they call a runt. And then the maximum Ethernet size is 1,518 bytes, and that would mainly be included in all your data. That's where all your data is going to take up all that space. So a minimum, if you just sent your preamble, these frames, and then the minimum data, it's going to be 64 bytes. And then the maximum that you can send for one is a 1,518. So let's look at Ethernet MAC address. The Ethernet MAC address is represented in hexadecimal. And so you're going to need to be familiar with hexadecimal and how hexadecimal operates. So I've got videos on binary, and I've got videos on how to convert binary to decimal. I do not have any videos on hexadecimal. I need to create some of those, and I may get those in the future, and I'll put links in here if I do have them. But if you look on the playlist for this Netacad course, if you look at my playlist and you look for the 5.1, you'll see my binary conversion and an easy way to do binary conversion from decimal to binary. And what I'll just simply say on this is just you need to remember that decimal is base 10, binary is base 2, and hexadecimal is base 16. Hexadecimal is base 16. So we count from we count from 0, and then when we get to 9, instead of starting back over with 1 0 like we do in the decimal counting world, we use the letter A to represent the number 10 in the decimal side. So to represent 10, we use the letter A, and then B, C, D, E, and F, and that gets us to 16. And remember, 0 is a number, so we start at 0, we end at F. So a combination of these numbers can be a number. So instead of writing out 15, or the decimal number 15 on there, because remember, 0 is a number, so 15 is the 16th number. So instead of writing out 15, F is 15. I shouldn't have written 16 throws you off, excuse me. That's actually represented by 15, but it's the 16th digit. That's where I want to clarify there when I wrote a 16 on there. That's representative. That's a comparison of the 15. Let me erase that. That's a comparison of the 15 decimal number over here. But that's the 16th digit. There's 16 places. So if we were going to convert that, if we were going to write the letter F in hexadecimal, that's representative of the decimal number of 15. In binary, that would be 1111. And how do we know that's what? Well, because we know how to convert. So, binary 0 is 0000. We add a 1. We add a 0, 1 because the place value of 2 here, place value of 2 plus 1 is 3. Place value of the next one over is 4. 4 plus 1 is 5, and so forth. And again, I've got a video that shows how to do that much easier, but you should be able to just look at binary numbers on the small ones and know what they are. So for example, this one right here, you know that's 1, 2, 4, 8. So you know that's 8. And then 1, 2, 4, 8 plus 2 plus 1, 10, 11. And then so 8 plus 4, 13, 14. 8, 9, 10, 11, 12, 13, 14, 15. Yeah, 8 plus 4 plus 2 plus 1 is 15 decimal. 0, 1, 1, 1, 1, or 15. So we use hexadecimal. To not make this any longer on this part here, we use hexadecimal to represent our MAC address because we can write large numbers using hexadecimal, but they do get converted, or they can be converted to binary on here. So this is just continuing it on down here. So if we do 2 sets, so if we say the hexadecimal number of, so if you see the hexadecimal number, let's just take a little number 0F here. So 0F, if we take that hexadecimal number, If we convert that to binary, that's 1111, which we know is 15. 8 plus 4 plus 2 plus 1 is 15. And then over here on the decimal side, we know it's 15. But if we take FF, FF is not 16 plus 16, or it's not 15 plus 15, it's not 30. So what we do is we calculate the first F, the first block, which is 1111, which is 15. And then the second block goes, which is 11 is 15. And then that's actually 255. And how do we know it's 255? Because we can do our place values. 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. And we add all those together, and that's 255. So, and plus when you work with subnets, in subnetting, you know that 8 places and all the ones are filled in is 255. That's 255 places that we fill in. So as we get into larger, so as you can see, as we get into larger numbers, we can represent the decimal number of 255 with just FF. And then, you know, we can add one more, and then that adds another block, and that makes a larger number. So we can get increasingly large decimal size numbers into a small space using hexadecimal. So when we look at our hexadecimal MAC address, it's broken down into 2 parts. You have your organizational unique identifier, or your OUI. Those are given to the manufacturers of the NICs, the network interface cards. Those anybody that's going to manufacture a vendor, they go to the IEEE and they get a OUI number, and that's the first 3 bytes. Must be the vendor's assigned OUI, as assigned by the IEEE, and then all the MAC addresses with the same OUI must assign a unique value in the last 3 bytes. So what would happen is if I was a vendor creating network cards, I would go to the IEEE, I would get my first 3 numbers from them, and in this case it would be 0060-2F. Now remember, that's hexadecimal. And then the last 3 blocks would be what I assigned. And so I would probably start off with something, you know, small and then go larger, but we've got a large block of numbers that we can use based upon those 3 sets of characters there, and it's 24 bits long. So we have a fairly large set of bits. So based on or set of numbers. So based on this unique information here and this information that's assigned by the IEEE, we're going to have a unique number that's identifiable to our card. And it's supposed to be hard-coded, and it is for the most part. It's hard-coded, but you can spoof MAC addresses. There's software where you can spoof that and make it look like something different, but that's how the MAC address is broken down. Now, when the frame is processed, when we do frame forwarding with a MAC address, let's say H1 computer is wanting to send a packet, and so our source is, we're going to say is all B's here, and then our other source over here is going to say we're going to send all C's, and this was going to be all D's, B's, C's, and D's. And so they know when they send, so if the source is all A's and the destination is all C's, when it sends out on the network and it says, okay, well, I'm B, so I don't need C, so I'm going to ignore it. I'm going to see that first frame. When that frame comes to me, and I'm going to see the source, or I'm going to see the destination first. I'm going to read that. So H2 is going to read that. Then it's going to read the source, and it's going to say that doesn't belong to me. I'm just going to drop it, and I'm not going to even pull up this data. I'm not even going to accept it, and so it doesn't get forwarded through. So what happens is the network interface card, or NIC, looks at the information. It looks at the destination, sees where it see if it belongs to that card or not, and then it passes it on up the chain if it does belong to it, and it starts reading the rest of the frame. If not, it just discards it. So when we're looking at MAC address representations here, when we do an ipconfig all on a computer and we look at our physical address there, we're going to see our MAC address, and you can do this on your own computer. You can pull up a command prompt and you can type ifconfig or ipconfig depending on which operating system you're on, and it's going to pull up some basic information. It's going to say here is your physical address, and that's the MAC address, and remember that's the OUI that was assigned by the vendor, and this last number was the unique identifier assigned by the vendor. So the OUI was assigned to the vendor, and you can look those up, by the way. So if you go and look up OUIs and you look up the first block of numbers here, you can actually go look those up and see who actually manufactured that. and you can find out more information. And I have done that in the past when I was had a strange network card, didn't know where it came from, and this was back in the days when you had to find drivers. We couldn't find drivers for these cards, and so we had to go out on the internet and look for who the manufacturer was and look to see when it was manufactured and who it was, when it was manufactured, and what drivers did it need. And so you can do that sometimes with so how the MAC address works with either unicast, broadcast, or multicast. So in a unicast, it's going to send it out, and it's going to say, here's my destination, here's my source, here's my destination. It's going to send it out. If it belongs to that server, so it says, okay, that does belong to me, so I'm going to go ahead and accept it. I'm going to read the rest of the information. I'm going to go ahead and read the IP information. I'm going to read the data, and I'm going to read all the read that information, and it's going to go through. But if it's a broadcast, it gets sent to everybody. So that destination MAC, it's all Fs, and when you see an all F or when it's all ones, it's going to send out to a broadcast, and it's going to get broadcast all of them. And that's why in the networking world, when you have an IP address and it's all 255, 255, 255, 255, that's a broadcast that on the when you send that out, because that's all ones across there. But then when you have a multicast, that's only going to certain particular ones. So you can have a group of them that it's going to, destination MAC, source MAC. And so a multicast is going to go to just specific members of the host. Okay, so let's take a quick look at LAN switches. LAN switches they operate at the layer 2, and they do more than what a hub does. A hub really operates at the layer 1. It just forwards packets on. It doesn't really read those. But you also have to remember that you have hybrids. Sometimes you have hubs that act like switches, or they do some functions of the switch, and then sometimes you have switches that do a function of a router. They're a hybrid, and they do some extra routing functions that other switches may not do. But we're going to talk about just basic plain switches and what they're doing. So using the MAC address table, the switch uses the Ethernet, or an Ethernet switch is a layer 2 device, or when you hear the word layer 2, you're going to know for the most part, most of the time, it's going to be an Ethernet switch. It uses the MAC address to forward frames or make forwarding decisions, and it's sometimes referred to as a content addressable memory, or a CAM table. Sometimes you will hear that, but rare, but you could hear that. So when the packet or the frame is sent, to learn the address, the port and the source MAC address are added on there. And what it's going to say is it's going to send it through, and it's going to say, I don't have this source MAC address, and it's incoming ports of our table, so I'll add it. So it builds a table on there. And then what happens is the destination MAC is not in the table, so it goes ahead and builds that in the table as well. And then filtering frames, it can filter a frame, because it can say the port and source MAC address are added onto the table. I don't have that source MAC, so it's going to add it on there. So then you're going to have the ability to build a table, and then it's going to be able to filter frames for you then. So it does do some filtering. It doesn't do routing, but it does do some filtering. And then that just goes on through, and I'm just going to go through it real slow here. So port and source MAC address are added. And then you have that information. So now the first computer can send from 1 over here to 4, and 2 and 3 don't even really need to read that, because it's going to get passed. It's going to basically filter that on there. So switch forwarding models, there's two different methods, or two different ways of switch forwarding. You have store and forward and cut through. Cut through is faster. What it does is it reads the first part of the frame. It recognizes where it needs to go, and it sends it on through. It doesn't read the rest of the information. It just forwards it right on through. It's faster. It reads the first part of the frame, and then it sends it on. But a store and forward, what it does is it computes the whole frame, or it reads the whole frame, and it looks at the CRC to make sure the frame got through. So this one is just going to take it and send it on. Doesn't care if everything's there or not. It doesn't care. It's the honey badger of the method. It just sends it through. Don't care. The step store and forward is going to look at the whole frame to see, did it come through, all of it? Did it come through properly? And then if it didn't, it's going to re-request it, or it's going to send a message back to say, did it come back, or that it didn't go through. But it's what it does is the switch looks up the destination address, which determines the outgoing interface. Then the frame is then forwarded to the correct port. So cut-through switching, there's an expanded model of it here. and some of the features of it. It's lowest, what we call latency, low level of latency. So it immediately forwards a packet. It just goes on. It's what we call a fragment-free switching. Switch stores the first 64 bytes of the frame before forwarding and then sends it on. So, and that's based on the fact that most network errors and collisions occur during the first 64 bytes. So they've just designed it to work really fast. The memory buffering on switches, and this is where you have the memory and then forwarding, but you have port-based memory. That's where frames are stored in queues and they're linked to specific incoming and outgoing ports. And then you have shared memory, and that's a memory buffering deposits all frames into a common memory buffer, which all the ports on the switch share. And that's why sometimes you will reset your switch, or you'll reset your your router too, but you'll reset your switch because it'll clear all that buffering out, or clear all that memory, and it'll clear those tables, and then and it should be clearing them on their own on newer switches and the newer software, but still, you might have to do that from time to time. So when we talk about switch port settings, if you recall back in the Chapter 4 videos, we talked about half duplex and full duplex. Well, if PCA is sending it full duplex and port 1 on the switch 2 is only working in half duplex, you're going to get, you're going to have a bad time because they need to communicate in the same duplex, whether it's duplex, half duplex, or full duplex on there. And then the speeds to get negotiated, so it has a common speed. So if this side is 100 megabits and 10 megabits per second, megabits per second, not bytes, bits per second, and this one is 1,110, it's going to go to the highest one that it can find and then find the common ground. So it's not going to send it 1,000 megabits over here because it won't be able to handle it on that side. So it's going to find the size or the speed that it can negotiate. And this is what I was talking about with the full duplex versus the half duplex. Full duplex is just sending its packets, sending them. It's not waiting on the return because it can communicate both ways. Well, this can only communicate one way at a time, and so it can only go one way at a time. So if it's trying to send a packet and a packet's coming in, it has collisions. So you're going to have a bad time if they're not synced up on the same type, whether it's full duplex or half duplex. Now we also have what we call auto MDIX, and I think I mentioned it on a previous video, that you have devices that will auto sense what type of connection you have. And so most of the newer devices will auto sense, and it'll say, okay, is this half duplex? Is this full duplex? What speed can I send this at? And then it will negotiate that and then start forwarding. Now the last thing we're going to look at on here is the ARP table, or the address resolution protocol. You need to be very familiar with the ARP, or the address resolution protocol, so you understand what it is and what its role is in the network at the layer 2 level. So the difference between the MAC and the IP address, there's two primary addresses assigned to a device on an Ethernet LAN. You have your physical address, and that's the MAC address. That's your layer 2. And then you have your logical address, and that's your IP address. So again, remember when we looked at your physical layout and your logical layout? Well, this is where that comes into play a little bit more too. You have your logical address, and that's your IP addressing. That's your layer 3 and above. That's used to send packets from the original source, and that allows us to do routing. Your MAC address does local area, and it sends it through the switching. And so this is communicating on a local LAN here. Let's blow this up. Make this a little bit larger here. Make this larger here so we can see it. So you have your original source, and it's trying to go through. It's going through a router here, and so it reads the frame. It says the destination is here. The source is here. Well, I can't get that on the local network. It's just not here. I don't see that, so I'm going to forward it through to the next router, and then it's going to go through, and it's going to negotiate that, and it's going to say here's where the IP address is supposed to go based on the IP source and destination. So once it gets up to that level, it's going to skip over this, and it's going to look for the source IP, which is your layer 3 once it needs to be routed. So ARP. Just a quick look at ARP. It's the address resolution protocol, and it is a way to do on a local network, and we talk about this on the switching at a layer 2. So H1 here needs to send information, but it doesn't have any IP addresses. So I don't know the MAC address of the device that has the IP either. So it's going to send out a request, and it's going to send out an ARP request. It's going to say, hey, here's my ARP information. Here's my address. And can everybody else report on what their ARP address is? So what it does is let me back here. There we go. So what it's going to do is it's going to send out an ARP request, and it's going to send that out, and all of these are going to report back, and it's going to say, oh, hey, I got your ARP request. Here's my ARP information. I'm going to build an ARP table. So you have that ARP table built, and each one of those tables then are going to have that information listed for those devices that it can see on the network. If it gets to a router, there's an ARP table on the inside of the router. Let's say that that's a router there, and it's going to see the ARP information for that router, and it can send it to there based on the ARP information or the ARP request, and you'll hear that in the network. So the functions of the ARP table, it's used to find the MAC address that's mapped to the destination IPv4 address. If the IPv4 address is on the same network as the source, the device will search the ARP table for the destination v4 address. And if the v4 address is on a different network, the device will search for the v4 address on the default gateway and send it through that way. So if it locates the v4 address, its corresponding MAC address is used as the destination in the frame. So if it locates the address in the same network, it'll use the MAC address. If no entry is found, the ARP request is sent. And when that sent device needs a MAC address associated with a v4 address, it doesn't have an entry in the ARP table. It requests a message that includes the target v4 address, the target MAC address, and the ARP request is encapsulated in an Ethernet frame using the following header information. You got the destination MAC address. That's the broadcast address requiring all Ethernet NICs on the LAN to accept and process the ARP request. So it basically sends a shout out, and it says, "Hey, I'm over here. I've got an ARP request. Everybody needs to respond to me. Everybody needs to tell me what they're." So it's like standing in a room of people and says, "Hey, my name is Bob. What's all your names?" And so everybody introduces themselves. And so Jane and Sue and Mary and John all send back and say, "Hey, my name's John. My name's Mary. My name's Sue." And then Bob records that information and says, "Okay, now I know who everybody is, and I can send that information on." If you're in the course, if you're in the Netacad course, there's a video demonstration on these, so you can just check those out in the Netacad course. And the device with the target v4 address and the ARP request will respond with an ARP reply. The ARP reply message includes this information here. And then the ARP reply is encapsulated in an Ethernet frame using the follow header information there. And then lastly, when the v4 address is not on the same network as the v4 address, the source device needs to send the frame to its default gateway. It sends it there, and then the layer 3 gets read, and then it gets forwarded on. And then when it gets to the other side, it gets back into a network with ARP tables being built and MAC addresses. It can use MAC addresses in. Okay, so if you need to remove entries from an ARP table, there's an ARP cache timer that removes ARP entries that have not been used for a specific period of time. And you can set that, but usually that's just the default. Commands can also be used to manually remove all or some of the entries in the ARP table. You can flush your, just like you flush your DNS cache, or you can flush that, but you can flush your ARP table. Usually you can do that by restarting a device, but you don't always want to go and restart a router or restart a switch. But that's one way to do it. If you do a restart on a device, it's going to flush that information and flush that memory. But you can also, there are commands out there and if you do the show IP ARP table, if you do that command, you'll get this response here. And that's the following ARP A, and that'll show you the full information on there. Some issues that you have with ARP is that if all the devices are powered on at the exact same time, you're going to get ARP broadcast flooding. Most networks, the larger network, when you have 100 meg or gigabit LAN speeds, it's not going to be that big of an issue. But if you have thousands of computers all coming online at the same time, or devices coming on, you could get some collision going on. So that's just, it's very unlikely, and you have to slow the network down a little bit, but it's not going to crash everything. And so if all the devices are powered on, they're all going to be requesting. You can also have somebody spoofing an ARP. So you could have somebody that's running software that says, "Hey, I'm going to send an ARP request out, and I'm going to pretend to be a default gateway." And so now those ARP requests that are going to come back in, it's going to say, "Oh, wait, this is a default gateway over here, so is this." So now when I send my request, and I can't find it, I can't find where I'm supposed to go to, so I'm going to send the rest of that packet over here to this computer here as a default gateway. And then they sniff that traffic and gather that traffic in, and then they can collect it. Okay, so a summary of this went about 30 minutes on this video. Apologize for the extra link on there, but I knew I could get the whole chapter in one video. We looked at Ethernet, we looked at how switches operate, and we looked at the address resolution protocol, or the ARP, and how those ARP tables are built. That's the end of this video. If it was helpful, go ahead and subscribe to the channel if you want to see future videos in your updates. If you have any questions, you can leave a comment below. And my name is Jason Johnson, and thank you for watching.